if you're keeping up with your homework assignments in Chapter 4, you're getting pretty good at analyzing open system problems that are steady state, steady flow. Might be one inlet, one outlet, might be multi-inlets and multi-outlets, but you're getting better and better at that. This video has to do with a type of problem that would be assigned near the end of Chapter 4. And so this video sequence might be a bit out of sequence, but what I want to do is cover this because the last few videos have been about the fundamentals of the first law of thermodynamics. And so it makes sense for me to cover this type of what we call transient open system problem in this video. Your textbook has a section called transient processes or transient open system processes. When I was going through as an undergraduate and ultimately graduate school, we referred to this category of open system as uniform state, uniform flow. And I'll give you some more details about why we call it uniform state, uniform flow near the end. But let's go ahead and get started. And this is an example of a homework problem that may be assigned, and it's really good to use as an example, is when you look at the sketch. Well, let me try to introduce the sketch. We've got a rigid tank, and I've shown my control surface in red dashed line here. Now that tank has a pipe connected to it, and so there is a supply of steam and a steam pipeline at a known pressure and temperature, and a valve that you can turn on and off admits steam into this vessel. Now, initially, the vessel has got 30 psi saturated vapor steam in it, and somebody opens the valve, cracks that valve open, and so steam from the supply line starts sneaking into this tank. And then finally, there's a pressure gauge on the tank, and the pressure reads 40 psi. And the question is, how much heat is added or rejected during this process? Okay, and so let's think about what would we do to get started on this. The solution is not clearly shown. At least it's not clearly revealed to me on how to attack this problem. So let's look at the problem. We know we're looking for heat transfer, and what can we say is true and not true? Well, one is it's undergoing a process. The contents of this tank is it's undergoing a process, 1 to 2. Now, would you say this tank is an open system or a closed system? Well, it can't be a closed system because we're admitting mass into it. It's not a fixed mass. So one thing we can say is it's an open system. Now, we're going to test for steady state, steady flow. I see mass flowing in, but I don't see any mass flowing out. So it cannot be steady state, steady flow because there's one inlet and no outlets. So it's definitely not steady state, steady flow. So what do? Oh my gosh. So I can't apply that fundamental steady state, steady flow to this problem at all. Nor can I go back and apply a statement of the first law for a closed system because it's not a closed system either. So we've got to figure out an approach here. And the approach is going to be disclosed to you in section 412. The textbook calls transient analysis. And in 412.1, it derives the mass balance, the continuity equation for this process that you just saw in a sketch. And then 412.2 it derives the energy balance, or in other words, the first law of thermodynamics for this type of process. And I've plopped down a screenshot of the textbook equation 425, which is a statement of the first law. And the thing is, what I want to do is I'm going to try to show you how to derive that statement of the first law. Now, if you're interested in physically seeing what a transient process is, And the fact, and open system, I've tried to go down in my workshop and give you a visual demonstration of a transient process where I'm draining my compressed air tank. And my memory is that what I do is I think I write down the pressure. See, I've got a little pressure gauge on my tank, and I believe what I do is I write down the pressure as time goes by to demonstrate it is not steady state, steady flow, and it's not, it's an open system and things like that. So if you're interested in looking at a physical demonstration of a transient process, go to my Thermodynamics Fundamentals playlist and find Transient Process Demo. And so I got to brace you for something. So I'm going to try to show you a derivation of how to get to that equation 425 rather than just blindly accepting it. And I'm hoping that it can help you better understand how to attack the problem. So this is a sleep alert for you for this video. So there's a nice clip of people enduring a derivation. I think I have the same effect on one of our cats, little Tigger. And so this is a great shot of him sound asleep. So I may have the same effect on him that I would have on people going through a derivation. First, let's derive the continuity equation for this type of transient process. So I've tried to go back and come up with a sketch that's more generic rather than the example problem I gave you of a rigid tank with one infeed. So my generic example of this transient process is going to be a piston and cylinder, but not exactly a closed system because I've got I've got multiple inflows and multiple outflows. And on my sketch, I'm showing that I'm adding some heat, some number of kilojoules, and I'm doing some amount of work, kilojoules, and I'm starting at some beginning state 1 and ending state 2. So that's a pretty good generic sketch of what we got. Now, what I'm going to do is just plop down a statement of conservation of mass that you can kind of figure out in your head. You don't have to go through, I don't think, any science to do this. How would we express conservation of mass? How is mass conserved for this open system problem? Well, let's just come up with an expression for the final mass. The final mass is at least the initial mass, isn't it? M2 is at least M1, okay? Plus, if mass is coming in, you'd have to add the mass that comes in to M1, wouldn't you? But if mass is leaving, when mass is leaving, you'd have to subtract mass from M1, and that's what enables you to calculate M2. So we have just derived by common sense 101 a statement of continuity for this type of transient process. Okay, we're about halfway there, or a third of the way there. So I hope I've convinced you that this is a statement of continuity of conservation of mass for this transient open system problem. Okay, now let's go back to that general statement of the first law of thermodynamics for any open system. So we're going back to equation 415. That is the general statement. That's your ultimate fundamental of the first law for an open system. Do you remember I went through a trick where I rearranged equation 415 so we could have a better feel for boundary phenomena on the left-hand side of the equal sign and then the other terms on the right-hand side of the equal sign? Remember, the right-hand terms were the rate at which the energy of the control volume changes. Well, let's think about our problem at hand where we were filling a tank. We started with an initial mass, and then we're filling a tank from a supply valve. So that would be dE dt as time goes by, some in between state 1 and state 2. And then here it would be the sum of masses that left. In our example problem, there's nothing leaving. That would go away, minus the masses that are coming in. We only had one flow in, but you get the idea. We're going to start with this. So I just repeated that on the next slide. Let's work on the first law, see if we can derive the first law for process 1 to 2 for that open system, piston, and cylinder. All right, so I'm going to write down what we had. Q dot minus W dot equals, there's dE dt. Okay, so, oh, and we've, for at least, let's strike out the kinetic and potential energy terms for the piston and cylinder that's sitting on a desktop, right? So it's not flying through the air. It's not going up or down during this process 1 to 2. So let's just strike those out. Okay, so we're only dealing with this enthalpy term that's leaving and this enthalpy term that's entering tied to the m dots. All right, next step. So the next step, I've got to pull a little bit of a mathematical trick. I've got to go back to calculus class, like freshman calculus, refresh my memory that Q dot is the mathematical expression for Q dot is del Q in dt. So in other words, the rate at which heat is added to the system. So Q dot is del Q in dt. W dot, same thing, del W dt, sort of the time rate of change of work going into the system. So it's a little bit of a mathematical trick. dE dt of the control volume, we're going to leave alone. This m dot, this mass flow rate, it's all about the dots for an open system. But what I want to go back with my mathematics is that we could express m dot as dm dt, the rate at which the exiting mass is being squished out of the pipe, okay? dm dt is another way to say mass flow rate. Same thing, dm dt going in is another way to say m dot. Okay. I hope you're not asleep yet, but this is another statement of the general first law, okay, for our situation. Now, the next step on the next slide is what I'm going to do is I'm going to integrate the left-hand side with respect to time. So in other words, left-hand side, dt, integral of that. Right-hand side, integral, dt. Let's see how that shakes out. We're going to get there pretty quickly. Hopefully you're still awake. All right, so I just rewrote my statement of the first law. That's the general statement of the first law. Looks a little different because the dots are all gone, all right? But now, instead of dragging through slide by slide for every term, I want to give you some examples of how we would integrate. How would we integrate this term, del Q dt, with respect to time? Here's my example. I would integrate from state 1 to state 2 of del Q in dt. Wow, now I'm going to look, wow, I can cancel out dt and dt, so I've just got the integral of del Q in from 1 to 2. Wow, that's sort of like integrating an ordinary differential, and so the answer is Q in kilojoules from from state 1 to state 2. Okay, let's look at this next term, the integral of dE dt of the control volume. I write that out. I integrate it, dt from 1 to 2. The same thing. Look at this. The dt's cancel, so I've got the integral of dE. Well, that's just E from 1 to 2. Well, that's E2 minus E1. And so now remember for your system, and we've thrown away, we're not going to have any potential or kinetic energy change. So do you see that E2 minus E1 becomes capital U2 minus capital U1? Okay, so and now let's see, our mass flow rate terms. M dot is dm dt, but same idea. These dt's are going to cancel. So the integral of the mass exiting from 1 to 2 is simply the mass that left, me. So now, instead of dragging you through all the terms, you get the general idea that a statement of our first law for this transient process is Q in kilojoules minus W out in kilojoules equals U2 minus U1. We'll figure out how to figure out U2 minus U1. plus the sum of the masses that left times the enthalpy leaving at those pipes minus the sum of the mass that's coming in times the enthalpy state in for those various pipes. This is the statement of a first law for an open system undergoing what I call uniform state, uniform flow transient process. So there's some special needs that the book does say in text. So in narrative form, it says what I'm going to say in this. I just want to make it clear what the textbook says, transient process. Okay, but anyway, this now you see how to derive this statement of the first law that was basically given in one of the equations in the textbook in that section I showed you. Qn minus W out equals capital U2 minus capital U1 plus the sum of the masses that left times the enthalpy leaving minus the sum of the masses that came in times the enthalpies in. Okay, thus the derivation. It looks like little Tigger has woken up from his nap. And so now we can get down to the part of, now how would we quantify these things? So even it's an intimidating looking formula. Here was my sketch. Here's the textbook expression, 425. I hope that you can quickly see that so I'm doing the same thing. I'm just moving my terms around the equal sign. So we have a better feel. Left-hand side is the boundary phenomenon, Qn minus W out. Okay. Now let's look at the next step. Qn minus W out is capital U2 minus capital U1. How would I calculate those? Well, that's just M2 times little U2 minus U1. M1 times little U1. Okay. Plus the other terms, the sum of the masses that left times the enthalpies leaving at those things, minus the sum of the masses that are coming in times the enthalpies coming in at those inlet states. Okay, now it does turn out that this is a powerful relationship, and this makes me go on a sentimental journey. Okay. And let's see what I've got. Oh, there we go. This will be a good place for me to reminisce about my own student experience. So what does USUF mean? Well, it means it's an acronym for uniform state, uniform flow. And here's what that means, that all of the I states and E states, they stay the same throughout. So in other words, the pressure and temperature, in other words, the state of what I'm circling here, at all times during process 1 to 2, it's the same pressure and temperature. For example, maybe over here at the E state, the same idea is that the pressure and temperature at this state, E, is the same, it's constant. Pressure and temperature is the constant from state 1 to state 2. That's what uniform state and uniform flow. So for example, from state 1 to state 2, when I open the valve, I get some mass flow rate going in, and that mass flow rate stays constant through the whole process. The integral of that mass flow rate is mn. Okay, but during the process, the mass flow rate is a constant number. Thus, uniform state, in other words, pressures and temperatures and specific volumes are all the same in between the two beginning and end state. Uniform flow, the mass flow is coming in, mass flow is going out. Those rates are constant during the process as well. Uniform state, uniform flow. So this is a very valid first law of thermodynamics for open systems undergoing a USUF, uniform state, uniform flow, transient process. So not necessarily any transient process, but it's got to be uniform state, uniform flow. This makes me reminisce about my own academic experience. I'm going to have to tell you, we had a couple of, I remember as an undergraduate being assigned about 2 or 3 homework problems like this. I will report to you right now that I remember that I did not get to the finish line on any of those homework problems. So I didn't get to the finish line on them. And due to good luck, my professor did not assign this type of problem in a test or exam situation. So I would not have been prepared to undertake this problem in a test or exam situation, and thank goodness I was not assigned it. So I guess in a lot of ways I was rolling the dice, and I came out okay. But do be aware that in a number of sections, there is a possibility that you will have a problem like this on a quiz or a test or an exam. So I want to kind of give you fair warning about that. Now you say, well, what is this guy creating these videos? He's such a dum-dum, he couldn't even figure out how to solve these thermo problems. I will tell you that I got better at them when I went to graduate school. So when I was taking graduate level thermodynamics, this was an expected part of the master's level curriculum. It was on tests and the exams, and I gave myself enough practice, and then I asked enough questions in class to be able to solve these problems to get through and do pretty well on the tests and the exam. So it did take me a while to master this technique, but it wasn't until master's level that I got good at it. Now, I'd like to strongly recommend that in my homework solutions playlist, you look up problem 483. So you see, this is very high. It's near the end of chapter 4. This is the solution to that tank filling problem. The other interesting thing about this particular video is I worked through all the numbers for problem 483, but I've also given you some, after I solved the problem, I'm going to give you at no extra charge some tips on the reverse problem. In other words, instead of having a tank filling situation where mass is going in, I give you some tips on how do you handle something for a tank with a pinhole leak in it. That would be a tank draining problem. So very similar, but also different. And so I work you through the first law and the continuity equation for the tank draining problem. So if you do look at this video and you do some work and do some practicing, that will put you in good stead for being at least pretty well ready to undertake a problem like this in a quiz or a test or the exam. So I don't want to give you a false sense of security that you will not have one of these simply because I did not have one of these as an undergraduate in 1973. So times do change, priorities change, and so do be aware that you may well have a problem like this in a quiz, test, and exam. Well, that catches us up. The next set of videos I have planned for Chapter 4 would be illustrating types of open system problems. And my memory of what I have planned is essentially illustrating problems that are steady state, steady flow, open systems. So I don't know what's coming up next because I haven't looked at my plan sheet, but I do hope it'll be something of interest to you, and I certainly encourage you to keep watching the rest of the series of videos for Chapter 4 because they may help you undertake a good number of your homework problems, at least get you some ideas on how to draw a sketch, how to get started, how to write down the first law, how would the first law apply to this or that.